You should know that electrostatics, according to Wikipedia, that I use just because I did classical studies, is a branch of physics that studies slow-moving or stationary electric charges. Specifically, it deals with electrostatic fields and phenomena that take place in electrostatic fields. That is, actions between electric charges, electrical induction, polarization, etc. Everything's clear, isn't it? If you want to deep the subject, please don't ask and check directly on Wikipedia since I'm not able to tell you more. Very good. But the question now is, why am I talking about electrostatics when I don't get it at all? The answer is quite simple, because today we will address a problem in which the electrostatic attraction plays a very important role. Today, in fact, we will talk about flocculation phenomena within ceramic mixtures that involve these kinds of attractions. We will discover different mechanisms, offering a general picture about the actions that we can take to prevent or avoid the problem. I am Davide Trentini, and this is Apparently Invisible: Chemistry in Ceramics. Let's start, as usual, from a definition. For sure, you already know what are flocculation phenomena that can affect ceramic glazes, or, as we will see, ceramic mixtures. Nevertheless, here is the shortest definition. Flocculation phenomena consist of chemical-physical process of a colloidal system within which the solid part tends to separate, leading to flux in suspension. In chemistry, this is the stage that follows the coagulation process, during which the particles stick together in small clusters, so-called flocks, that may precipitate. Speaking about ceramic mixtures, let's see what happens during flocculation phenomena and what we need to know to trigger the opposite process, that is the deflocculation process, to face the problem. But before doing that, let's make a quick recap about ceramic mixtures. Since it is the main character of the episode, I would like to make a list, once again, of the most important steps to which ceramic mixture is subjected and that turn raw materials into high-performing ceramic surfaces. To put it simple, here is the list: grinding, sieving, stocking, atomization, pressing, forming. Okay, before entering the core of the problem, let us briefly review these important stages. Ceramic mixtures before the forming phase, during which the atomized powders are pressed or compacted, undergo to a wet grinding process that involves the use of grinding waters, mostly deriving from recovery and groundwater. At this stage, the inorganic raw materials, that of course are sands, clays, feldspar, etc., together with the water, form the slip, also called barbottina. The grinding process takes usually place by means of Alsing mills, and once the barbottina has been produced, it is sieved and then stocked in tanks, where it rests under constant stirring to avoid possible gelling or sedimentation phenomena. After stocking, whose duration can range according to the different needs of the producers, the slip is nebulized by means of spray dryer to rapidly and violently evaporate the water content, thanks to the use of very high temperatures. The evaporation process turned the drops of the slip into tiny hollow spheres that make up the atomized powder, finally ready to be pressed or formed. Good. After this short recap, let's go deep by defining from a chemical point of view the barbottina, or slip. The slip is a water suspension of clays that can be more or less plastic according to the needs, and other inorganic raw materials such as feldspar or sand. We talk about suspension and not about solutions, since the ceramic slip is a mixture in which the solid part is finely divided and dispersed in a liquid part, that is the solvent, in order to avoid too rapid cementation phenomena. The amount of solid part of a suspension is usually smaller than the liquid part. And now, the next question is, what are the main features of clays? Well, clays, for their very nature, generally tends to show an important thixotropic effect that must be managed and removed to let the slip properly flow. That means, in other words, to work it properly. But what is thixotropy? Thixotropy, in simple words, is a feature of pseudoplastic fluids to change their viscosity over time when subjected to a shear stress or a solicitation moving, for example, from a passive state, we could say almost solid, to a fluid state. What does that mean? This means that ceramic slips, due to their structure, are exactly marked by this feature. In fact, while they are resting, they seem to be gelatinous, but when they are stressed by an external force, such as, for example, a simple stirring, they usually become fluid, and this is not always good. To better explain, please think about the ketchup. The ketchup, when it's resting, is very compact and hardly to move. If you want to use it and get it out from the bottle, you must shake it. That means that you have to apply an external force. And this is exactly the clay's behavior. Good. Let's now look closer at the reasons why thixotropy must be faced, also highlighting the basis of the flocculation phenomena, and we're doing starting from defining the clay's morphology. We assume that clays are minerals made up of octahedral and tetrahedral sheets of aluminium oxide and silica. Think of them like layered paper sheets. The sheets can be arranged in many different positions according to the type of clays, but in any case, between one sheet and the other, we can find some cations of a different nature. Regardless of the kind of cations, once the clay has been dispersed in water, the octahedral and tetrahedral sheets tend to expand due to the water that filters between the gaps, that is, the space between the sheets. This movement may sometimes lead to the release, within the suspension of course, of those cations that are in the gaps. Good. Let's now add another important detail about the electric charge of the clay micelle. You should know that the sheets are mainly marked by a positive charge on their border and by a negative charge on the two surfaces, the upper and the lower surfaces of the clay sheet. This means that the micelle is marked by two different charges at the same time, positive in the border and negative on the surface of the sheet. This morphology, especially in case of low water amounts within the suspension, usually produces an electrostatic attraction between the positive and negative charges that leads to an increasement in the viscosity value of the system. In some extreme cases, the system jellifies, negatively affecting the proper development of the production process. So, what should be done? Well, to restore the system, and therefore to produce the flocculation effect, it is important to make micelles and particles in suspension move. And to make this happen, there are some important mechanisms to consider that are the basis of the flocculation process. What are these mechanisms? How do they work? Now we will try to give answers to these questions by using a very simple approach. Since the topic is absolutely complex, I will try to give you short and very easy info that you can deepen, of course, by contacting us. So I apologize in advance if I simplify too much, but as you know, we try to talk also to those that are not experts. That said, let's start from the first of the three mechanisms, speaking about electrostatic repulsion by cationic exchange. The multivalent cations with a double positive charge, such as calcium or magnesium, for example, or with a triple positive charge, such as iron or titanium, are marked by a very high charge, capable of breaking the strong negative charge present on the borders of the micelle. However, this negative charge is important and somehow necessary to ensure the repulsion force between the micelle, providing them with the proper flow. And in this regard, I invite you to think about the repulsive force that takes place between two magnets with the same charge. The mechanism is very, very similar. So, the question is, what action should we take when this balance disappears and flocculation phenomena arise? Well, the addition of monovalent cations within the system, such as sodium, promotes the replacement of the multivalent positive charges with weaker electric charge. This specific cationic exchange decreases the positive charge on the micelles without neutralizing the negative ones. And that's the basis of the de-agglomeration and therefore of the lowering of the viscosity values within the system, that in turn restores the right condition of the ceramic mixture that can be properly used along the production line. Let's now address the second of the three mechanisms, talking about steric repulsion. The steric repulsion is usually produced by using polymeric dispersant made up of inactive molecular chains, that is, molecular chains that do not produce any interaction with clays and raw materials, but that, however, contain at the same time functional groups able to promote an interaction. The edges of these molecules interact with the suspended particles of the slurry, increasing their distance. In other words, polymeric dispersants bind themselves together with the particles through the functional group in a specific position that produces the proper distance that is requested to let the particles flow one on the other, avoiding the electrostatic interaction that usually arises between the positive and negative charge of the micelle, and this phenomenon leads to the viscosity reduction and therefore to the flocculation effect. Good. And now we finally close our review speaking about the third and last mechanism, that is complexation. Complexing agents, and so even in this case we are talking about chemicals, consist in particular molecules provided with functional groups with specific atoms, such as oxygen, that provide the system with a very negative electronic charge. This charge ideally attracts multivalent instead of monovalent charges. But what does that mean, or what does this lead to? It means that once complexing agents have been added to the slurry, they release sodium, that is monovalent cation, attracting multivalent cation, such as calcium, magnesium, iron, or titanium. The final result of this process is the removal of the multivalent charges from the system and the introduction of monovalent charges, promoting the cationic exchange, increasing the distance between the particles, decreasing the viscosity value, and therefore reducing the flocculation effect. And with the complexity of complexation, a nice play of words, we have come to an end. Despite the necessary simplification, I hope I've given you interesting information and food for thoughts. Of course, if you want, we are always at your disposal to deepen the subject within our labs. As usual, I also remind you that you can listen to the previous episodes on the main platforms or on our app that you can download for free on Apple Store or Google Play by typing Z and S Ceramco or Apparently Invisible. Between positive and negative attractions, I live. See you soon.